Hi everyone, Dr. Madi here, and in this video I will show you how to install ROS2 Humble interface and run the robot in simulation and reality. So let's get started. In this activity, our primary objective is to install both ROS and Python ROS interfaces to be able to control our robot arm. As our intention is to use ROS2 Humble, we have already taken the necessary steps to set up Ubuntu 22.04 in the previous videos. It was essential to select this specific version of Ubuntu since ROS distributions are OS specific. Pincher X100 robot arm comes with a ROS2 interface package to make our lives easier. The robot model argument in the launch files for this arm is PX100, so this is the code name that we will use for this robot arm. PX stands for Pincher X, and 100 is the length of both the forearm and upper arm links in millimeters. You can verify this with your robot arm. Here are the steps to install ROS2 Humble on desktop and laptop computers running Ubuntu 22.04. First, open a terminal by pressing Ctrl+Alt+T, then run the commands sudo apt update and sudo apt upgrade to update and upgrade your Ubuntu operating system. After that, copy, paste, Ctrl+Shift+V, and run the code shown here to install ROS2 Humble. This code will install the curl package on Ubuntu. Curl is a command line tool and library used for transferring data with a URL. When you run this command with administrative privileges, sudo, it will prompt you to enter your password to confirm the installation. Once you provide the password, the package manager apt will download and install the curl package and its dependencies on your system. In the following code, we are using the curl command to download a shell script named xsarm amd64install.sh from a GitHub repository and then save it as xsarm amd64install.sh in the current directory. The chmod +x command is used to change the permissions of a file, making it executable. By running chmod +x xsarm amd64install.sh, you are granting execute permission to the xsarm amd64install.sh script, allowing it to be executed as a program. Once you've executed the previous command, you can run the script using the following command with the Humble option or argument. We specified the version of ROS2 that we want to install using the D flag. After running this code, it will ask if you want to install the perception packages and MATLAB ROS API and type Y, meaning yes for both. Then it will give you an installation summary to verify that everything is correct. Mine looked like this. Check that the ROS distro is right and that it will install Perception and MATLAB modules. The last line shows that it will create a workspace in my home directory by that name. If everything is correct, type Y to confirm and continue. It can take up to 15 minutes to install everything. To verify that everything is installed successfully, follow the following steps. First, check that the UDEV rules are configured correctly and that they are triggered by the U2D2 controller. For this, check that when U2D2 is plugged into a USB port, the port name is TTYDXL. This command searches for any device files in the /dev directory that contain the string TTYDXL in their names. These device files are associated with communication ports for Dynamixl servos. As we learned in class activity 1, Dynamixl is a brand of smart servos commonly used in robotics and mechatronics projects. The communication with these servos is typically done through serial communication using a USB to serial adapter. The device files with TTYDXL in their names are created when the adapter is connected to the system and represent the virtual serial ports associated with the adapter. Now check that the ROS packages are installed correctly. First, we should source the setup.bash file for the specified ROS distribution. Then, we should source the setup.bash file in our robot arms workspace. And finally, we list the installed ROS packages and filter the output to only show the packages that contain the string interbodics in their names. The fundamental core ROS2 interface packages that you should confirm are installed are these that I show here. If everything checks out and the installation is complete, restart your computer to ensure that all changes take effect. In this part, you will learn how to work with the ROS2 interface and get the robot up and running. First, we need to source our workspace. This will set up the necessary environment variables and configurations for the packages installed in that workspace. When you run source, it executes the commands in the specified file, allowing you to access the packages and resources in the ROS workspace. Sourcing the workspace should be done in every new terminal to properly configure your ROS environment. But there is a way to get around this, and that is adding the previous line of code to the end of the .bash RC file, so that you do not have to do this every time. Access the file in the home directory and make sure that you activate it to show the hidden contents. Next, open up the robot's virtual model in RViz and play around with the joint state publisher. This code will launch the XSARM description launch file from the package Interbatics XSARM descriptions with specific parameters like the robot model and the graphical user interface for publishing joint values. Ctrl-C will terminate the session from the terminal. Now connect to the physical robot arm and run the following command. This command will launch the XSARM control launch file from the package Interbatics XSARM control with the robot model parameter set to PX100, which is the code for our robot arm. By running the previous command, you will see that all the motors on the robot will be torqued on, and you cannot manually manipulate them. You can torque off the motors by executing the following command in another terminal window. Note, make sure that the robot is in the rest position, or else it will collapse when running this command. This command will call the service torque enable and send a request to disable torque for all joints in a group. This group includes every dynamic cell motor in the manipulator. After this, you can manipulate the arm and the gripper freely. Also, make sure to note that by moving the physical robot, the virtual model in RViz also responds accordingly. The following command can show you the list of the ROS services that this torque enable service is one of them. There is also a control panel in the graphical user interface, where you can interact with services and topics instead of the command line in the terminal. First, torque on the robot again. Then enter the robot's code in the robot namespace and hit Update. Home/sleep publishes a joint group command to the joint group topic. You can see a list of topics by typing this command. From the group name, choose All for all joints, including the gripper, or Arm for all joints but the gripper. Then, for example, hit go to Home Pose to go to the robot's 0 position, and after that, go to Sleep Pose to go back to the sleep position. You can also do other things, for example, interacting with other services like torquing on and off the robot, which is the torque that works with torque enable service that you can see in the service list. For torque off, make sure that the robot is in sleep pose or you are holding the robot arm, preventing it from falling. The others are services that can be found in the ROS2 service list. If you want to hold a robot in a certain pose, torque it off again and manually get the robot to that pose and torque it on again. By doing this, the motors are again torqued on and the robot can hold that pose. Now that you feel comfortable working with the physical robot arm, hold on to the robot so that it does not fall, and press Ctrl+C in the first terminal to shut down all nodes. You will see that the robot is torqued off and manually place back the robot in its sleep position. So by the end of this part, you should know how to interact with the virtual robot through Interbatics XSARM descriptions package, how to interact with the real robot through Interbatics XSARM control package, become familiar with some of the concepts of the ARMS ROS packages like different topics and services that you have available.